Well, welcome back, folks. Looks like we can get started officially. Today's class is kind of a sad class in a sense because we're finishing off chapter one. It seems like one of those chapters that just keeps going and going and going. But then we'll be on to neat and other interesting ideas. Chapter two is going to be about matrix operations, adding matrices, subtracting them, multiplying them. And we can't say dividing them, but we can say multiplying by their multiplicative inverse. So we're not covering a lot of chapter two, but the ideas that we're going to look into there are going to be some of the major ideas, talking about matrix inversion being one of the fundamental ones. Well, oh, didn't mean to scroll there. Well, the major thing we're going to do is finish up our discussions on linear transformations, look into a little bit more interesting applications on their use, and we'll push this definition further and talk a little bit more officially about the standard matrix A and how to construct it. But any questions at all, folks, before we get started today? Okay, so roughly jotted down, here are the two properties for linearity. In the notes, it's typed out a little bit easier to read, so the same properties down here in the definition. And we usually paired this together in the last notes as well, the theorem from section 1.4, because the properties look so similar that if we relate these ideas together, define transformation T so that it goes from Rn into Rm by T of a vector x in Rn equals a matrix A times X, then all of these properties up here are suddenly relevant. They're the same properties of linearity, verbatim, essentially. So we call that matrix A the standard matrix A of the transformation T. And the theorem 5 above tells us automatically, if you define a transformation in this way, it's linear. You don't have to go through the work of checking part 1, part 2. All that work is essentially done for us instantly. So we'll practice this. We did this kind of example in the notes in section 1.8, but this is just another look at how this goes. It's an operation that goes from R3 into R3, defined horizontally in this notation in this way. To show T is linear, you could work pretty hard and work out these properties. In fact, some people have done that occasionally in the homework, but this is what I would encourage you to do. Rewrite it as T of X equals AX. So another look at how that goes algebraically, you could call this, where the red dot is, just T of X if you preferred. The step is optional, just expanding and relating to what we have there informationally at the red dot. X is just the vector of components, x1, x2, x3. And it has to have three components because it came from R3 itself. Then the output is defined in this kind of a clunky way. It's all there completely correct, but if we want to deal with the matrix, it's a good skill to transfer from this notation into a matrix notation. So I'm going to go directly at it like this. Kind of made that matrix a little taller than I needed. Let me fix that. I'm just going to put down first a column vector using all these entries. So 2x1 plus x2. Entry 2, we have to go carefully according to the commas. Negative x1 plus 5x2 plus 3x3. And entry 3 is 4x1 minus 2x2 plus x3. Then that's the same transformation, just a different look at the new notation here as a column vector. Now, here's the part, spoke a little bit earlier when I mentioned this earlier. Here's the part where I go directly into the matrix times the vector x1, x2, x3. So same vector as the input we saw there. Instead of decomposing this as a linear combination, really you might notice the punchline when we did this in the section 1.8 notes. All you really did was pull coefficients. So column 1 is all the coefficients relative to variable x1. So 2, negative 1, 4. Likewise, column 2 is going to be 1, 5, negative 2, because those are the entries relative to x2. Finally, column 3 would be 0, 3, 1. So this whole matrix right here is the standard matrix A of the transformation T. this is now in the format of A times X. This works for every single vector X. We didn't choose a specific input. We let X be arbitrary as X1, X2, X3. So we can say since T of X is nothing but a matrix A times the vector X, T is linear. That deserves an exclamation mark because that's the use of the theorem 5 up here. We just relate all the information to the standard matrix, and then it flows through the definition automatically. We've proved linearity without really directly even looking into the definition. But any questions at all, folks, with this kind of a refresher problem from section 1.8? Okay, the major part of the notes that we want to discuss today are determining if the transformation T is 1-to-1, if the transformation T is onto, and how that all relates to the standard matrix A when the transformation is linear. So working through the notes, sometimes it's really fast to find this standard matrix A. Other times it can be a bit of a chore. And so we need a bit of notation and a good theorem that's going to assist us, depending on how the transformation is defined. It was defined in a nice way. It told us exactly what it did to X1, X2, X3. If we go down to this one, it's less nice. It says T is the mapping that rotates every vector in R2 counterclockwise about their origin through the angle theta. This is linear. You're going to have to take my word for it. We'll find the standard matrix. And that's going to be the proof of linearity. You might know the punchline to this already, especially if you watch this video here. It just tells you how to rotate vectors. But if you didn't know how to do that, you want to work with these things, E1 through En. So that's new notation, and it gets defined right up here. I think the identity matrix has been discussed really kind of very briefly when it came up in several contexts. Usually it's when we had a system of, say, 3 equations, 3 unknowns, and there was a unique solution. This matrix popped up. So the identity matrix, we can either write it as I or In. It's like the number 1 in matrix multiplication in the next chapter. It's always a square matrix, so notice the n by n there is excluding 3 by 2 or 4 by 5. It has to be 4 by 4, 3 by 3, 2 by 2 at minimum. And this is what it looks like. The main diagonal are all equal to 1. Every entries off the main diagonal are equal to 0. And so if we were to write down, say, I2, it would look like this. It's going to be a square matrix of size 2 by 2. It says entries on the main diagonal, but that would be the entry that goes here and then diagonal that way down. So it starts up at the top, going left to right, and moves to the bottom. Main entries are both 1s. All of their entries are 0s, so 0, 0. So this would be I2, or just simply I, if we didn't need to write that down, if it was clear from the context. Main diagonal are these entries right here. And so that's how we would write down an identity matrix. It gives us an idea of what E1, E2 through En are. EI is a column vector containing 1 in the ith row, 0 elsewhere. So this vector that we wrote in, this one would be E1. It contains a 1 in the 1th entry, 0s elsewhere. This one contains a 1 in the 2nd entry, 0s elsewhere. So this would be E2. So that's the rundown of the definitions and notation so far. Any questions, folks, about the identity matrix at the moment? Okay, another way to write the identity matrix could be I. If I want to be specific what size I'm writing in, we could put in an I3. Then this would be E1, E2, E3. But E1 just says put a 1 here, 0s elsewhere. E2 as a vector just says there's a 1 in the second position. Here it is, so 0 is elsewhere. And E3 as a vector says 1 is in the third position, 0 is elsewhere. So really, we pretty much did the same thing as what the second sentence was doing. The identity matrix A has 1s on the main diagonal, 0s elsewhere. So it makes E1, E2, E3 seem kind of weird in a certain sense. It's not clear why we're emphasizing them, but that's what they would look like at the moment, just writing them down as vectors. So this is E1, just for the strict reminder, this is E2, and this is E3. Any questions about those vectors so far? Okay, they turn out to be pretty special vectors. Later on, we're going to say, let's focus on the set of 3 vectors in R3. The set E1, E2, E3 is linearly independent in R3. How do we know? There's a review problem. It's because there's a pivot in every single column. Or in other words, if we solve I3 equal to the 0 vector, it would only have the trivial solution because there's no free variable, but that's once again because pivot in every single column. So we could say it's linearly independent in R3 since I3, which is formed from those particular vectors as its columns, has a pivot in every column. And we can say even more. Notice if there's a pivot in every column and it's square, there's also a pivot in every row as well. So we can say the set E1, E2, E3 spans R3 since there is a pivot in every row. So the review portions that we were looking into are for spanning, we have a pivot position in every row. That was theorem 4 from section 1.4. And for linear independence, we had a lot of formulas and definitions, but the punchline was a pivot in every column gives us linear independence. And we might also say, well, what's special about all of that? Well, if you have something that's linearly independent and something that also spans, let's also underline R3, the space is important, then we can say it's not just a random set of vectors. We'll call this a basis. In fact, it's a particularly important one. This means E1, E2, E3 is a basis. And this one particularly has a name. This one's called the standard basis for R3. And if we plug the standard basis vectors in that particular order into a matrix, we get the identity matrix. So lots of new concepts and comments, but it's nice to see the tie-in for information we've done before. That's kind of the role of sections 1.8 to 1.9. It's kind of reviewing the entirety of chapter 1 to date. Well, any questions at all, folks, with the new notations or ideas so far? Want to fix how I underlined that now that I'm looking at it. Okay, another use for these vectors, the standard basis vectors, is this theorem. Let's hide this trigonometry for just a moment. This theorem that we were looking into, theorem 10. So theorem 10 is a powerful construction theorem. It says, if we have a linear transformation going from Rn to Rm, there will be a unique matrix A. So this exists and we can find it, such that T of x equals A times x. That's the standard matrix of the transformation. And the way we can find it, no matter how weird the transformation is defined, and this is pretty weird when you think about it, all we have to do is take into the first column t of E1. The second column is going to be t of E2. The fourth, fifth, nth column will be t of the last basis vector, En. So really that's all we have to do to build a transformation. We didn't do it in the last problem because really if the transformation is defined in this way, the standard thing to do is just re-express it and the matrix pops out. It's too strong of a theorem for something that just needed simple algebra. So we needed something more nasty, and this is my version of more nasty, a transformation that does a clockwise rotation through the angle theta would be a great way to exhibit the use of theorem 10. So let's give this a try. First, let's take a really close look at what this does. It's the mapping that rotates every vector in R2 counterclockwise about their origin through angle theta. So the fundamental vector space for the domain and looks like codomain is both R2. So to get a quick visual, let's draw this out. Here's my look at R2. T is going to map it back into R2. So same space, but now it's the codomain on the right. We can indicate the transformation T this way, domain into codomain. But sometimes when we're doing these sketches, we put the label T right on the arrow to say T is mapping from R2 into R2 in that way. So lots of different ways to indicate how the transformation T is working. Next thing we'll work with are the actual basis vectors. E1 would be right here. I'll say that's 1 on the x2 axis. I should label, or excuse me, the x1 axes. I should label the axes just for, I think, possibly my own sake as well. So if we label this as 1, 0, that would be this position here on the x1 axis. On the x2 axis over here, that's E2 equaling 0, 1. So now we have to rotate by that angle theta from this part of the problem. So the transformation T is going to act on these two vectors. And if you can tell what T does to just the two basis vectors, it defines the entire transformation because it constructs the standard matrix A. So that's the powerful thing about this theorem. And that's also the special role of a basis. The basis is like the smallest amount of vectors we needed to define the entire transformation. So let's give this a try. On the right, E1 started right here. E2 started right here. I'm going to make the angle theta just be a simple acute angle, just so that the diagram doesn't get too busy, but it can be any angle in the clockwise direction. It can wrap around multiple times. So I'll let this, looks like 30 degrees, but maybe it's 31 degrees, who knows? Here's my angle theta. I'll indicate it maybe this way. So I'm rotating the vector E1 by that angle theta. All vectors are just rotating that way in the plane. So E1 moves around to this spot. We'll call it T of E1. If we can say what T of E1 is, our job is done. Likewise over here, this vector rotates as well by the same angle. So make it about the same angle off from the x2 axis. Just to make this stand out, I'll use purple. This is now the angle theta plus pi over 2. Well, the 90-degree rotation is the pi over 2 part. The theta is the extra amount it rotated. And so this vector E2 rotates by the mapping T, ends up right here. Here's T of E2. So that's the setup so far. If we can come up with T of E1, and then again for T of E2, our job is done. Really, it's just a review on trigonometry, defining the sine and cosine functions. Anyone happen to know what T of E1 would be by the diagram so far?
Would it be U1
Sorry, say again.
Would it be U1 cosine?
Close, it would just be the cosine theta sine theta without the E1, exactly.
Okay, yeah.
Yeah, so here it's just a 1-0, but when we go here, that's what it comes exactly as you said. Good call, this is just cosine theta, sine theta. Reason for this is, if you look closely, E1 is a distance 1 on the x-axis, rotating by theta. That's a distance 1 from the origin. All of these points lie on the unit circle. X1 squared plus x2 squared equals 1. And coordinates on the unit circle are, by definition, first entry cosine of the angle, second entry sine of the angle. I'll take this line off because it gets a little bit too busy. Maybe let's make it a dash line. Imagine that's a circle, so we'll go with that. A little bit of artistic interpretation will help. So if we can do the same thing with T of E2, we'll just throw it all into the matrix A and our work is done. So this is column 1 of the standard matrix. Then finally, T at E2, same exact concept. This is an X and Y coordinate, or a first component, second component on a unit circle. Through the definitions of trigonometry, it's going to be cosine at that angle, which happens to be theta plus pi over 2. Down below, it's going to be sine at that same angle, theta plus pi over 2 again. Finally, this is why we have the review from trigonometry up above. You could leave it just like this if you wanted to, but this is kind of clunky and ugly to use as a formula. You may as well simplify it as much as you can, and that's going to be through the addition formulas that we have above. Let's put that down below just as a quick reference. So now expand this stuff out through the addition formulas. It's random to do trigonometry like this out of nowhere. Transformation T isn't there, just a vector. That's kind of the fun thing about linear algebra. It interfaces with all sorts of stuff all at once. Trigonometry entering into linear algebra is pretty natural in a certain sense. So first, addition formula for cosine goes cosine theta, cosine pi over 2, minus sine, then sine theta, sine pi over 2. Same thing, but for the sine function, this one will go sine theta, cosine pi over 2, that's a 2 there, plus cosine theta, sine pi over 2. Then it simplifies even more, kind of nicely, because cosine pi over 2 is 0. This is gone as a term. This is gone as a term. Sine pi over 2s are 1, so in a certain sense, just that part cancels. That might be a weird thing to write in, though. That might be lost in translation. Sine pi over 2 is 1, so we just get negative sine theta here. It's 1 here as well. Forgot to close the delimiter there. So we just get positive cosine theta. We're done with the addition formulas, so we can leave them back where they were at the very top. But now we're back to just the theorem. Theorem 10 said all you need to do to find the standard matrix A of this transformation T, a rotation transformation, is find the mapping T at E1, find the mapping T at E2, and that's exactly what we have down below here. So when it said find the standard matrix of T, our job is essentially done. We just have to construct that matrix. We'll say, therefore, T of X equals AX, where A is equal to T at E1, T at E2, which by substitution goes cosine theta, sine theta, and then negative sine theta, cosine theta. So that matrix there is any clockwise trans or rotation through the origin. Well, any questions at all, folks, getting that matrix there? Okay, one use you could do already with having this now as a formula is you can just pick any theta you'd like Let's suppose we take for an example, let's end the problem here and just add a related concept. Let theta equal pi over 2, then that's a 90 degrees rotation. Then A would be equal to cosine pi over 2 is going to be 0. Sine pi over 2 is 1. Sine pi over 2 is 1, so this becomes a -1. And then cosine pi over 2 is 0. And let's check this out. Let's take t at E1 and see if we really move 90 degrees and end up here on the x2 axis. T at E1 is going to be A times E1, and it better be because we said that's the big punchline here of defining this matrix. So A is going to be 0, 1, -1, 0. E1 puts a 1 in entry 1, zeros elsewhere. It's good to review here just on its own, a matrix times a vector. On row 1, we multiply corresponding entries with this column vector, and we will get 0 plus 0. Then for the second entry, we'll take 1 times 1 for a 1, plus 0 times 0 for a 0, and we get a 0, 1, and that is exactly this entry right here. So if we apply the mapping t to E1, we rotate by pi over 2 degrees and end up in E2. And this would work for any angle theta whatsoever, so kind of a cool trick in a way. Well, any questions at all, folks, running through that theorem or working with this particular transformation?
If we were rotating clockwise, would it just be negatives?
Yeah, absolutely. So the same thing can extend by just putting in a negative pi over 2, and you'd get the same exact result, absolutely. Other questions so far? Okay, same kind of ideas can work in R3. It gets a little bit clunky like you can imagine, so take a look at this video if you're interested in computer graphics in R2, R3, what rotations might look like as a standard matrix here as well. It has a pretty nice, really dense just rundown of all these kind of ideas. Well, next thing we're going to get to is the big parts of section 1.9, one-to-one and onto. Looks like we're starting with onto. So these are going to be our next big topics. There's really a lot to say here. These definitions on their own are not really easy to parse when you look at them. There's a particular way our author likes to say it. Sometimes they can be rephrased if there's just a better version that you would feel like makes most sense to you. Let's maybe hide one-to-one for the moment and focus on what we mean by an onto mapping. So we're taking a transformation going from Rn into Rm. It's said to be onto Rm, the transformation T is onto, in other words, if for each B in Rm, so we're talking about the codomain, it is the image of at least one X in Rn, Rm be the domain. So that's a pretty decent way to say it. I think I typed this out of the book pretty much verbatim. You can say this slightly differently. An alternate version would be, that is, T is onto if for every B in Rm there exists an X in Rn such that T of X equals B. Takes me longer to say it, but somehow in my brain, this makes a little bit more sense. Maybe it's because it says is the image of at least, and I just wrote it T of X instead of using the image language. I think our author is just trying to get us used to seeing it this way. Not a bad idea, since sometimes textbooks do write out definitions in this kind of way. And if you just translate it into your own words that might make a little bit more sense, that's a great way to learn the definition. And by the way, if you've seen this definition before, you might have learned different terms for it. A synonym is that onto in other math books, sometimes the more fancier ones, is sometimes called surjective, which is a French word. So the French have a lot of influence on to mappings. So sometimes even English textbooks call these surjective mappings. I'll just go with onto, but this could help with reading elsewhere. And a quick visual still helps because this is just purely an analytic way of looking at it, but it's kind of a geometric thing you want to think about. So let's do the rare thing of just plotting a couple functions to get a feel for this. First thing I want to plot is something that is not onto. So if we write y equals, let's maybe do, how about t just to make it seem familiar? Let's go t of x equals x squared. Oh, and let me fix that. There we go. I can't necessarily say this is not onto unless I specify what the codomain actually is. So let me also further say T is going to map R to R. So I'm just using more simpler functions, ordinary real valued functions from a real domain. This would not be onto because it says I have to satisfy this. For every vector B in Rm, that would be the codomain, the vertical axis. There exists an x in Rn such that T of x equals B. In other words, the square of that x comes out with whatever number is right over here. If I plug in a number that's negative, that's not going to work out for us. Sure, if I take a number 1, then 1 down here maps to that value 1, but nothing in the negative end works. So this is not onto. In other words, T of x equals -1 has no solution x. But again, the domain and codomain are special ingredients here, and particularly the codomain. We change our view on this function, we can force it to be an onto one. Let's put this first down just as a particular example. So this is just us geometrically thinking about onto as a definition all on its own. Feels huge for some reason. Let me shrink that down. And take the same exact graph. The key thing about functions is in order to define a function, you have to say how it maps every element of the domain, but specifying the domain and the codomain is part of the definition of the function. So if I take it and write it this way, T maps R to 0 to infinity. If this is my codomain, it is an onto mapping because any element here on the codomain from 0 to infinity, there are domain elements, x, there's multiple ones, they're going to map to that right value, giving us a solution. So going this way, this is onto. So kind of tricky in a way. Oh, I shouldn't move that too much. Kind of tricky in a way. Does that make sense to folks, the differences between the two? Okay, so maybe just to add one more punchline. Geez, using the annotate is trickier than I thought. T of x equals b has solution. No matter what b you pick, you can take x to be equal to the square root of b. That works over here because I'm only picking non-negative entries. Doesn't work down here because I can't take the square root of -1. The whole process just breaks down. So codomain is a very particular part of onto. Essentially, all we're saying with onto is every element in the codomain can be associated with at least one vector x in the domain itself. If you can do that, if you can always solve T of x equals b, said differently, you have an onto mapping. So those are the two pictures that discuss the definition. I'll leave them down below just for a reminder if you want to take a look at the two versions later. Now we're in a bigger space. Those are just kind of related examples to think about onto. But our functions are going from things like R2 into R3 and so on. And one major key ingredient is we always want to assume our transformation T is linear. Those are the major ones we're studying because it's linear algebra after all. So let's make that assumption here. Assume T mapping Rn into Rm is onto and linear. Linearity changes things a lot for us. It's going to give us tools to determine if something is onto just right away. Whereas if you're working with the definition strictly and you're trying to show a transformation is onto, that can be a pretty large amount of algebra. This could take quite a while to get through. So assuming that T is linear means we get to do the following. There exists an M by N matrix A. Notice if we're going from Rn into Rm, the size of the standard matrix flips those dimensions around. It's now M by N, matrix A, such that this is the standard matrix A, so we'll have T of X equals A times X. So if we enter that into the discussion and assume that T is onto at the same time, it means onto is just this right here always has a solution. So let's say that next. Since T is onto, T of X equals B, you could say has a solution, but I'll go with is consistent for all B in Rm. So this is us emphasizing the transformation. If we wanted to, we can just swap in the matrix multiplication. This immediately implies it next. A times X equals B has a solution for all B in Rm. It's always consistent, or if you prefer to say it always has a solution. Then finally, we can go back here. Here's theorem 4 from section 1.4. We just verified part A. The matrix equation AX equals B always has a solution. This works for any M by N matrix A whatsoever. And we can conclude all these parts are now simultaneously true. In particular, A must have a pivot in every row. And that's the whole punchline to being onto as a transformation if you're linear. Let's put down that punchline. Therefore, by theorem 4 of chapter 1, A has a pivot in every row. And that's our whole big punchline. Being an onto transformation just means you know something about the pivots of this transformation. When you look into the standard matrix A, there's automatically a pivot in every row now. Relating our old theorem 1.4 back into this definition, this is the key way linear algebra seems to want to operate, at least in chapter 1, and specifically for these kinds of vector spaces. We can take any transformation, relate it to a standard matrix, and then just devolve that definition, no matter how technical, into something about pivots. This one's about pivots in every row. Any questions, folks, about onto transformations?
So those examples you gave earlier with the,
Yeah,
those weren't linear.
they weren't, no. These are just ordinary transformations from, say, R into R or R into 0 infinity. And the idea with these was just to give us kind of a picture in our mind's eye of what onto even looks like for just simpler functions. So yeah, those are just ordinary functions, not linear. Other questions at the moment? Okay, so this is one of our big punchlines so far. We're gonna have a theorem that's gonna summarize all this together. Part of the hard work about this work is just really thinking about what onto is. And the next one is thinking about what one-to-one is. So let's try this out next. Sometimes one-to-one feels like an easier concept. I think it just depends on the person. These are both pretty technical definitions on their own, even if the definitions are short and fast to write. So one-to-one next. It says a mapping T going from Rn into Rm, so not assuming linearity whatsoever, just an ordinary transformation. It's going to be one-to-one if each B in Rm, so we're talking about, because I don't want to use too much color coding, we're talking about a vector in Rm here is the image of at most one X in Rn. So the wording at most is pretty particular here. You might have had pictures in the back of your mind's eye on this one. One-to-one means an ordinary function from algebra would pass the horizontal line test, intersect only once at any horizontal line at most. But you know, it's a tough definition in this form. If we reword it like we did before, this is how a lot of definitions for one-to-one sometimes are written. Let's say T from Rn into Rm, that's an M there, is 1-to-1 if B being the image of a one most X in Rn, we can capture the essence of that by just writing out this. If T of X equals T of Y directly implies, let's say that in ordinary words, although the arrow would convey the same information, implies X equals Y. So we're saying if the outputs are set equal to each other, well, that might suggest that X is a preimage and Y is a preimage, leading to the same outputs. But if it's one-to-one, every output, T of X and T of Y, is the image of at most one X. So X and Y have to be equal to each other. So this is one way to convey one-to-one. And just like before, you might have read one-to-one in a different textbook. A different way to say one-to-one is just like surjective is onto, injective is synonymous with one-to-one. So if you're a fan of French, then this is what they would say in every French textbook, and they're so influential. We have it in a lot of English textbooks as well. Sometimes your textbook will just say injective and never say one-to-one. Well, quick look at one-to-one functions could be like what we did before. Oh, and I closed that out. Let me open another Desmos. First, let's do one that's not one-to-one. That could be, once again, T of X equals X squared. The reason this one is not one-to-one is if we pick, let's say, a vector B in the domain space, let's also give it a domain and range right out. We're going from R to R, so just a simpler ordinary function to get a feel for the one-to-one definition. This vector here, or this point here on the codomain, would be like each B and Rm part. And there are two values of X value here, a Y value here, that leads to that same value B. Looks like it's 3. Since T of X equals T of Y, and X is not equal to Y, T is not 1-to-1. It's 2-to-1, since two inputs, this X value and this Y value, leave to the same output of B. Looks like it's 3 once again. So that's what not one-to-one would look like as a quick graph using ordinary real valued functions. We can fix this and make it one-to-one really pretty fast by doing something like this. So here's the non-example. It's good to know when things don't fit in. So there's the example for that one. But let's fix this one. Suppose I don't want to change T of X equals X squared. But I want to force it to be 1-to-1 so that this is going to have x equals y. Well, you could just change either one of these. For onto, we had to change the codomain. We made the codomain smaller so that we force it to be onto. For 1-to-1, we can just fix the domain. Let's say we map t from 0 to infinity to r. We can force that to happen. It's our function. We can do whatever we want. In fact, if you want to invert the square root function, you have to do this, or else it has no function inverse. So we'll insist here that 0 less than or equals to x. And this is the function now. Now this time, if you pick a random vector, here's your b vector, there is at most one input x that's going to satisfy. So if t of x equals t of y, we know something about y automatically. It has to be equal to x. There's no other way to make this equation work out. Or let me write this in a slightly better way relative to the b and the x there. Let's say if t of x equals b, t of y equals b, that's the same thing as saying t of x equals t of y, but I want to emphasize the b that's up here as well. That it immediately implies x has to be y. T is 1-to-1. And again, the horizontal line test is fantastic if your functions look like these. Our functions don't look like that. They're going from like R2 to R5. There is no horizontal line test any longer. So this is just really us thinking about what does 1-to-1 really mean? What does it look like in familiar context from back in the day? Any questions with either graphs, the 1-to-1 or the non-1-to-1? Oh, geez, there we go. Well, now that we have those graphs, next thing we want to do is assume something extra. We're not going to go from R to R or 0 to infinity to R. We're going to go to bona fide vector spaces where the n and the m are at least 2, and we're going to assume linearity. If we do that, then we're going to have a better way to work through this kind of definition for 1-to-1. And here's what it's going to look like. Let's say here, assume T mapping from Rn to Rm is linear. This is pretty much the big punchline to the entirety of sections 1.8, 1.9. If you're going from these specific kinds of vector spaces and you assume linearity, you have a standard matrix. If we work with that standard matrix, we can relate everything we've done in chapter 1 just about to the new definition, 1-to-1. So let's say here, this means t of x equals ax for the m by n standard matrix A of t. And so that's a great way to get started. Now we want to find a simple way to address 1-to-1. Let's see, how can we do that? Let's take a look into this equation. Consider t of x equals the 0 vector. So that would be one place to get started. T of x equals the 0 vector can be rewritten as a times x equals a 0 vector. Oh, I think I forgot to write in one additional thing. I've got the transformation. We've got that it's linear. We have the standard matrix, but the whole discussion is about 1-to-1. So let's, just to be specific, say, also assume t is 1-to-1. Okay, so now we have 1-to-1 as well. We're considering a times x equals a 0 vector. And we know that this equation has the trivial solution. x set to the zero vector. It's a homogeneous equation, so it automatically have that trivial solution there. But if we say it's 1-to-1, then this vector right here, we find a good color to indicate it. That's just a vector b in the codomain space. It's the image of at most one x. Well, we just found that x. 1-to-1 says there's no other ones to find, so it has the trivial solution, and this solution is unique. Only one vector can map into the zero vector, t of x equals the zero vector. So ax equals the zero vector has the trivial solution and it's unique. That means the following. This implies ax equals the zero vector has no non-trivial solutions. They're just completely ruled out by 1-to-1. And the fact that the homogeneous equation here always has the trivial solution. But now if we have no non-trivial solutions, what would you say that would relate to? Is that linear independence or is that linear dependence? Anyone recall which way this would go? Absolutely. Having only the trivial solution, see if we have this somewhere in the notes. Yeah, right over here. If you have only the trivial solution, then the columns of the matrix A are linearly independent. So you could relate onto or injective mappings as being linearly independent. Or if you really want to, you just can jump into having a pivot in every column. All those concepts are now related to each other if your transformation is linear. If it's not linear, all that information is gone. You don't even necessarily have a standard matrix A whatsoever. So let's write down the punchline to this. We can say, therefore, if T is 1-to-1, then the columns of A are linearly independent. And so A has a pivot in every column. So that's our big wrap up of connecting all the dots through the content in chapter 1 onto, as a transformation that's linear, just means your standard matrix has a pivot in every row. And 1-to-1 means a pivot in every column. So these same kind of ideas just keep on coming back over and over and over again, which is kind of nice in a way. But it's also mysterious. It seems like it's hard to do something in linear algebra, invent a new definition that doesn't reduce down to the pivots. What's making that happen is those specific vector spaces. If you make them weirder, then these ideas can get a little bit trickier. And that's the big purpose of what chapter 4 is going to be all about. But here's the big wrap up, the big punchline to all these ideas. Theorem 11 says what we just said as well, and Theorem 12 brings into both onto and 1-to-1 mappings as well. First, Theorem 11 is telling us if your transformation is linear, then T is 1-to-1, if and only if that equation has only the trivial solution. So really you need to look into one equation to determine 1-to-1. Then finally, this is some comments we made before we started class. T being 1-to-1 means the columns of A are linearly independent, which just means at the same time, there's a pivot in every column. T maps Rn onto Rm. In other words, T is onto. Just means the columns of A span Rm. And that's the same concept as pivot in every row. That's kind of cool in a way to see linear algebra just connect those ideas so cleanly just to concepts about pivots. It means we could have talked about 1-to-1 and onto in section 1.2 when we were first talking about the pivots, if we just decided to make these definitions first for some reason. that probably wouldn't have been a good idea, but you can see that that would have been something that would have been doable in a way. Well, the next two examples that we're going to look at, similar to the homework problems, are just working with these theorems and these ideas. We have a transformation T defined in this slightly inconvenient way. All we want to know is if it is one-to-one and if it's onto. First thing we need to exhibit is, what is the standard matrix A? The moment we find it, our work is pretty much done. And we can get that standard matrix A essentially by just redoing the first problem on these notes. Just reformat the transformation T. We can rewrite this as T of X equals. I'm just going to come over here and rewrite this as a column vector. It's x1 plus 2x2. Row 2, or entry 2 in the column vector, is strictly 0, so I'll just put a 0 there. Entry 3 is 2x2 plus x4. Trying to be careful with the format. We skipped x3, so I'll put a little spacer there. And the last entry, entry 4, is x2 minus x4. So there it is as a column vector, also formatted so that the variables correspond to essentially columns. Now, using the same idea, first example, these notes, we can rewrite this in this way. This is going to be our standard matrix A. The x that we have right here is just going to be x1 through x4. Then pull coefficients to generate the columns. Column 1 would be 1, 0, 0, 0, because those are the coefficients relative to x1. Column 2 goes 2, 0, 2, 1. And this is weird. It's kind of a strange example. Column 3, the one relative to x3. Well, x3 never shows up, so it's just strictly zeros on this one. 0, 0, 0, and 0. Then for x4, we go 0, 0, 1, negative 1. So that's our standard matrix A. And now that we see that matrix A, our work is just about done at this point. Notice that A is a squared matrix. It's of size 4 by 4. Because one of the columns is a 0 column, we can say right away, the columns of A are linearly independent just because of the presence of that 0 vector inside there. You'd be using this part of the definition. So notice it's glued together by an if and only if. That means if it's linearly dependent, not linearly independent, then it's not one-to-one. So you could have also said there cannot be a pivot in every column if one of the columns is the 0 vector. So either way you'd like to go would be a great way to summarize. I'll go with the independence part. We can say T is not one-to-one since the columns of A are linearly dependent due to the 0 vector in column 3. And same other problem here with that row. If you had a 0 row here, you don't even have to do row operations with this any longer. But another thought is, if you have at maximum 3 pivots, then you cannot have a pivot in every row any longer. So this tells us the columns of A do not span. You might say, go this way, there cannot be a pivot in every row. So T cannot be an onto transformation as well. So we'll say next, T is not onto since there is, without any row reduction, probably 3 pivots, but we could say at most 3 pivots. Most 3 pivots with 4 rows. in A. So there is not a pivot in every row. And I wrote this argument slightly different. I didn't relate it to the column spanning because they're really equivalent kind of concepts. So if you just decide to end your discussion on there's not a pivot in every row, therefore it's not onto, that'd be a fine way to answer that question there. If you want to bring in it's not spanning, that'd be just fine. That's kind of what we did with this one. There's not a pivot in every column, so it's not linearly independent, which means it's not one-to-one. Well, any last questions, folks? Getting through this quick one here. Okay, well, we're nearly done with the notes. There's some optional reading that's towards the end of the notes, but I believe this last one is going to be our final example. After that, I had an application of time permits. I didn't think it would. We're slightly behind on our schedule. So I filled in some of the information that you can look into there. If you're really interested in what's interesting about one-to-one and onto linear transformations, there's even more reading down here. We show that two spaces, the set of complex numbers and the set of these matrices, are equivalent algebraic structures through something called an isomorphism. And we even relate it back to this matrix here being a 90-degree rotation, being the same thing as the concept of multiplying by the complex number I is also a 90-degree rotation of your complex number in the complex plane. So wild and crazy connections, but this is only if you want to do that reading. The actual textbook problems would end right here on example 5. So this is possibly where we'll finish up the notes as well. I've just restated the theorem, so we're learning them. We'll get a feel for how these go. And these are different kind of problems because we're not looking at the standard matrix any longer. We do know our transformations are linear and something about the domain going into the codomain. We want to see how we can relate this to concepts of one-to-one versus onto. And then part C, we'll see it again, but with a specific matrix, kind of just a summary problem. So here's the kind of thought about one-to-one. The domain is a four-dimensional space, R4, and we'll be really precise what we mean by dimension later on in the notes in chapter 4. So something that's four-dimensional is getting crammed down to three-dimensional space. You can make that happen in a linear way. There's no problem with that, except it couldn't be one-to-one. You have vectors essentially overlapping going to the same inputs, or the same inputs going into the same, or different inputs going into the same outputs. So if things go like this, it's impossible for it to be one-to-one. That's the geometric intuition, thinking in dimensions. And here's how we would show it. We use the fact that t is linear to say, from here alone, t of x equals ax, where a is, go to these dimensions here and swap the order. The size of the matrix A is 3 rows by 4 columns. So it has to be 3 by 4. And just a quick review on why that's the case. If you put 3 by 4 here, you can make matrix multiplication work if and only if x is of size 4 by 1. And it has to be of size 4 with 4 entries because that's the domain. X comes from R4. So you can always reverse engineer if you forget the trick to get the 3 by 4. So now A essentially looks like this. I don't know the entries, but I know what the size of the matrix is. I'll have 3 rows, 4 columns. And we can reuse an old strategy from prior notes. If you think about the maximum best case number of pivots, maybe not specifically in those columns, but by number, there is at most 3 pivots if your matrix is 3 by 4. So there is at most 3 pivots. You might have thought of this in a different way. There's another theorem that says if you have more columns, 4 of them, than entries per column, 3 of them, The columns are automatically linearly dependent. So if you thought in those terms, that's a great way to attack this as well. I'm emphasizing the pivots, it looks like mostly on this one. So if I said that there's at most 3 pivots, that means there's 4 columns with 3 pivots. The columns are linearly dependent. So the columns are linearly dependent, and A is not 1-to-1. It turns out this is impossible. It's all because we insisted the transformation is linear right here, and that's pretty restrictive. If you took this off, if it's just an ordinary mapping, you can make this 1-to-1. That's kind of amazing and fantastic in a certain sense. Nothing's going to stop you from making that work out, but it can't be done in a linear way any longer. Any questions with what's going on in this one? Okay, so a big takeaway here is that nonlinear transformations is kind of like the Wild West of transformations. It's almost as if anything goes. But the moment you insist your transformation is linear, there's some hard and fast rules that kind of matches with what your intuition would say. So similarly here, we're wondering if we can go from a 3-dimensional space and fill out a 4-dimensional space. Onto means every object in 4 dimensions has a way to map to it. For every b in R4, a t of x from here would equal that b. That turns out to be impossible if your transformation, once again, is linear. If it's nonlinear, you can make that work, and that's kind of amazing as well. In a nonlinear way, you can take a 3-dimensional space and expand it to cover R4 with the right transformation. But something goes wrong if you're linear, and let's explore why. Really, it's just a redo of the same kind of idea. We're just going to flip around these dimensions. So if we have the transformation as linear, then this implies t of x can be defined as a times x, where a is, this time, 4/3. So flip around the dimensions you see here, and that's the size of your matrix. Recall onto is going to say, the standard matrix A, the one we just put down, spans. What it'll span is going to be R4. Well, let's write down the 4/3 matrix. It would look like this. We don't know the entries, but we know the size of the matrix, and this is the schematic for putting down entries. 4 rows, 3 columns. Feels like deja vu, but it's just essentially the transpose of this matrix. We've interchanged rows with columns. If we look into the best case for pivots, once again, there's at most 3. You can't get a 4th pivot here if you have only 3 columns. So we would say there is, at most, 3 pivots once again. So there cannot be a pivot in every row. You could just jump right to t is not onto at this point, but if you want to, you can connect the dots. There's not a pivot in every row. That means the columns of A can no longer span R4. So we'll say that here just to connect the dots. The columns of A do not span R4. And this was such a big theorem, it's not a bad idea to just look at it once more. We have part D as false. The pivots do not occur in every single row of our matrix A. That means we cannot span Rm. The m is this dimension for R4. But if the columns of A don't span R4, that means the mapping T is not an onto mapping. There will be vectors inside R4 for which T of x equals B is inconsistent. We cannot actually hit every single vector if the dimension of the codomain is 1 higher or any amount higher than the domain space. So our conclusion here is then finally, therefore, T is not an onto mapping. Or we could just say T is not onto, or we could say T is not an onto transformation. Loads of different ways to say this. If you just say not onto, that's the big punchline with this one. So it's not one-to-one, it's not onto in either one of these cases. Really, it looks like if you want a linear transformation that is one-to-one, these dimensions have to match. That's going to be really the key punchline to all of this. If you want this, or hang on, let me think of that a little bit differently. If the dimensions do match, one-to-one and onto will be the same, but it is possible to be one-to-one, but not onto. I misspoke with that concept there, and vice versa. It is possible to be onto and not one-to-one. I think that's what's going to happen in this next one down below. But any questions with the quick rundown on parts A and B? Okay, one last one, kind of just a summary of what we've looked at before. We have T of X equals A times X. The matrix A is given to be this one. We want to know what is the domain, what's the codomain of T. So what we would do is write down the size. This is 2 by 3. This means T maps from R3 into R2. If you say it this way, you've told me the domain and codomain, so this is a fine way to answer it. If you want to be more specific, you could just write this out. Domain is R3, codomain is R2. Then same old questions as above. We want to know if it's one-to-one, if it's onto. Definitely not one-to-one though, right? The columns are linearly dependent just by the presence of the zero vector inside here. Because we're short on time, if we want to be brief, we might say T is not one-to-one. There is not a pivot in every column. Then when we address onto, there is a pivot in every row on this one. So we can say T is onto. There is a pivot in every row. And that's pretty much all we had to say about these two problems, or this last problem here in part C. There's so much more that we could talk about this kind of stuff. And if you know you're taking more algebra, maybe abstract algebra, maybe modern algebra, you probably would want to read the stuff on the bottom of these notes because ideas on isomorphisms would be coming back. In fact, we'll be looking into isomorphisms ourselves a little bit more. Once we're fully in chapter 4, we'll say what they're all about and actually use properties of isomorphisms to simplify a huge amount of linear algebra. But any last questions or comments at all, folks, with our conclusion so far? Okay, well, chapter 1's been fun. It's kind of sad to see it go. There's really so much more we could talk about. But chapter 2 is going to be fun in its own way. We're going to do something that looks more like how the course started out, doing more numerical kind of computations, matrix multiplications, matrix additions, and those kinds of things. So we'll start our chapter 2 fully when we come back on our Thursday's class. But have a great afternoon, folks. We'll see you all next time. Here, I'll trade you. Thanks.
And label these, I don't know, about that.
That'd be all right. No worries.